Hey, what's up, everybody? We're going to be talking about Power Lab 2 practice today. I'm going to do this in two separate parts. This first part is going to be an example one, the series example, and then I'll do a second part on the parallel example. So here we are. We have our problem, right? I'm going to be doing this on paper. You're going to be doing this on the computer. But let's talk about a couple things that I have out right now. First thing I have out is my metric prefix sheet. The second thing I have out is some white scratch paper. Then the third thing I have out is my calculator. And of course, we're going to need TinkerCAD for this as well. So I have my computer out, obviously. So the first thing we really need to do is we can basically ignore all the power stuff to start with. And we can just start off with like Ohm's law and Kirchhoff's law, right? So again, Ohm's law is E over I times R. Power is P over I times E. And we can really start to like look at this problem here. Let's see if I can focus this camera a bit better. So we know in this case that our voltage total is 9 volts. I'm pretty sure is true for all of these examples. We also know that according to Kirchhoff's law, states that in series, my current is the same and my voltage will add up. Okay, so I need to remember that. So I can't just write 9 volts across everything because the voltage is the thing that's going to change. My resistor 1 in this case is 100 ohms. Resistor 2 is 470 ohms. Resistor 3 is 2,200 ohms or 2.2 kilo ohms. So my total resistance is going to, and this is where you're going to put your screen capture, but for my example here, I'll do my formula here. Resistance total is equal to 100 plus 470 plus 2.2K. So that is equal to 2,770,000 ohms or 2.77 kilo ohms. So resistance total 2.77K ohms. So again, according to Ohm's law, we're looking for current. 9 divided by 2,770 is equal to 0.00324. So when I go to convert this to a metric prefix, I'm going to come over 1, 2, 3 to the right. So I'm making a number smaller, so I'm going to come down on my list, 1 box. So that's equal to 3.2 because the 4 is less than 5. 3.2 milliamps. All right, so again, that's our constant. 3.2 milliamps, 3.2 milliamps. Okay, so now we can solve for our voltage. Take this number, multiply it by 100, right? Because resistance times current is equal to voltage. So I'm going to multiply that by 100, and I get 324.9 millivolts. And then multiply my current times 470, and that's equal to 1.5 volts. And now I'm going to multiply that by 2,200, which again, biggest resistor here, by far going to use like the most voltage. That's equal to 7.1. And again, 7.1 plus 1.5 plus 0.3249 is equal to 8.92, right? And again, it should total 9. Pretty darn close. It's rounding errors, okay? So we're good there. Power now, it's super easy to come up with power at this point. It is simply, again, power total is equal to our current total times our E total. So in this case, our E total is 9 times 0.0032. So in total here, 1, 2, 3. My total power is equal to 28.8 milliwatts. Now, one thing, ladies and gentlemen, that I should definitely point out is make sure that your resistance total answer is right to begin with. Like maybe do that formula twice and just make sure you didn't put in any errors, because that error will like multiply throughout the whole process. But assuming that this is correct, all of my powers will equal roughly 28.8, and again, I can feel pretty confident. So once again, here, this is 324.9 milliwatts. So again, if I took that number and multiplied it by 0.001, or if I moved my decimal place 1, 2, 3 over, it's 0.3249 times, and in this case, my current 0.0032. Okay, so we're gonna get some small, like we're starting off with 28 milliwatts, so all of our wattage is going to be pretty small here. This is equal to 1.0 milliwatts. Okay, so we have 27.8 milliwatts left. Then we can say here 1.5 times 0.0032 is equal to 0.48 milliwatts, 0.48 milliwatts. So again, that's like 0.58 in total between these two. So it's like 23. So we know that this should be about 23 milliwatts in order to be correct. So 7.1 times 0.0032 is equal to 1, 2, 3. 22.7 milliwatts. And again, I just said it should be close to 23, which that really is. Again, rounding errors, but 22.7 plus 4.8 plus 1 is equal to 28.5 milliwatts, which again, we're off by a few tenths of a milli, which is like a few 10,000ths off. We're certainly within the realm of possibility here. Alrighty then. So I'm in TinkerCAD at this point, and I've already started to set up the circuit. Okay, I have a 9-volt battery. That 9-volt battery is connected to the positive and negative bus. I have resistor 1, which is 100 ohms. I have resistor 2, which is 470 ohms. And I have resistor 3, which is 2,200 ohms. And at this point, I've created like a circuit that, again, when we follow our negative electrons come through the bus, come across this wire. They come up 7, across resistor 1, up 11 to resistor 2, back down 15 to resistor 15, and from 15 back again. So if I were to start my simulation, nothing happens, but I do have power running through there. So the cool thing about this lab, unlike when we're measuring for resistance, current and voltage and multimeters, they work hand in hand. We can be measuring both of those things simultaneously without an issue. So when you go through to like set the circuit up, you are going to be setting up the ammeter and the voltage meters, and you're going to be showing me all of those values. So at this point, I have an ammeter set up and I have 3 voltmeters set up, right? So I just brought in multimeters and set them up. So I'm going to start to set these up. So I am going to put my ammeter down here. It could be off to the side. It can plug in too, okay? So now like the negative bus is plugged into 2 and the positive bus is plugged into 3. Honestly, I could even move this over so that like part of it's plugging into my circuit, but I am going to leave it outside of my circuit to avoid too much confusion. But again, we have to disconnect our circuit to put our ammeter in because an ammeter needs to be in series. So now our electrons are going to come down. They're going to come across this wire and they're going to go into the negative side. Then coming out from here to here is going to be basically the red wire, which is going from the positive to here. So again, negative, it comes through, and then it comes out over here. Honestly, because this is in the interim of the process, it's honestly not really like positive or negative at this point. I'm going to change it to yellow. It doesn't really matter. You can leave it here. So now if I were to start my simulation, I could see my amperage at least, which is measuring at 3.2 milliamps. And again, when we look at our answer here, it's 3.2 milliamps, and this is 0.25, which is interesting. I'm surprised I didn't round that, Anyways, okay, so coming back here, it's now time, I'm going to stop this. It's now time to start wiring in our voltage meter. So again, voltage is being measured in parallel, not in series. So we can leave everything connected as is, and we are going to connect all of these up to the individual circuits. So I have one positive end, or the negative end rather, on the same side as the negative is coming in. That's going to give me a positive number. And that surrounds the left side of the terminal and the right side of the terminal. Okay, so that's going to pick up the voltage for that first one. Then I'm going to come back again here. And again, I'm still in row 11. Okay, because row 11 is both the end of resistor 1 and the beginning of resistor 2. So there's row 11, and I'm going to connect from here to here. Again, that's going to be red. And then from here, again, this is going to go in row 15, and it's going to be black. And then this is going to go to row 19, and it's going to be red. So from here, we now, again, we follow in through here, we go through our ammeter in series, then we come through, we go through our circuit, and on each side of our resistor, we're going to be measuring the potential difference of voltage. All right, so when we start the simulation now, these are the numbers that we're getting. Okay, and let's just compare these to what I have down here. I can't really show you both very easily, but I can read it. So for resistor 1 right now, for my voltage, I have written down 324.9 millivolts. Here we're reading 325. So that's, again, slightly different due to rounding and whatever, but it's the same number. Next number here, I have written down 1.5 volts. This is 1.53 volts. So again, it's come out to like 1 extra decimal point, but it's the same number. And lastly, I have written down for this resistor 7.1 volts. This one is coming out to 7.14 volts. So again, different but the same. We would do a screen capture. Yeah, there we go. And when I go to do my screen capture, I would want to select basically all of the important information, including my battery and including all of this stuff. So when I come to like paste it into my document, so when I come into here and I come into this box where it says screen capture of circuit, remember you need to have the multimeter and voltmeter in there. And I go to hit Control V, it'll paste in. And again, I really want to see, and ideally it's in like order from like left to right. Resistor 1, resistor 2, resistor 3, you'd have all of that. Plus, of course, you would have all of these values written in above. Okay, so that would be problem number 1. All right, and again, we're doing 2 practice assignments, 1 in parallel, 1 in series. And then there's going to be 4 assigned ones for the lab. All right, so in the next video here, we are going to be talking about how to do the same thing, but in parallel. All right, so once again, this is Power Lab 2 practice assignment, problem number 1, part 1, series circuits.